Hello again, it's Phil Story, a network detective from Australia. I wanted to just revisit the packet timing chart this time and look at some of the highlight packet behaviours and show some extra features of the packet timing chart. Just a reminder, we're using NetData Lite and we're visualising IT performance. We'll begin with Kerry's slow web PCAP file and look at some of the HTTP 400 connections, and there's a couple of interesting retransmission timeouts that I'd like to show. After that, we'll go back to the PMTUD PCAP file and we'll look at some red and green packets. And while we're there, another RTO example. Here we are again with the HTTP PCAP file. And this time, we'll start with showing a right click, give name to IP address. Interesting. Of course, you can give it any name you like. And when we assign that, we get this table, which we can just get rid of. It says, do you want to save it? Yes, we do. And we do want to reassign names throughout the database. So now NetData is going to go throughout all the tables in the database that have that IP address, and it's going to add the name to it. We'll also see that because of the sort order here, this server is down at the bottom now. So the next thing is we'll just focus that again, and then we'll right click on that and chart records of this service. Now before we get started, I want to go over again this load data window. And it's very important this time that we tick this, transactions of another class. And I'll just do my other things because I always do anyway. Now this time we're only plotting the one server. And because we focused it, it's already set here. So this time, instead of loading all, I will load just the one server. And we don't need to clear data already because we're just basically adding to what's there. Now why did that matter? We'll find out shortly. Notice in the connections table we now have the server name, interesting. But if you click addresses, it'll change back to the address. So here's the performance chart, and now it's just got the transactions related to the server that we've called interesting. So whereas before we had an IP address up here, now that this server's got a name, the name will appear here. So just a side observation, we know from Kerry's video on the weekend that the problem here was that the DNS on the other side of a local proxy server wasn't working properly. And in hindsight, there's a bit of a clue here. So the first transaction took a long time. That would have been the one that sort of initiated the DNS. Then there's a couple of these guys that were longer, but after that we get back to normal because the DNS entry would have been cached. The first thing I'd like to talk about is these request unknown. Now here's one here and in the legend, and it's a red square, hover, we can tell that's that one. We could have seen the red square, right click, plot transaction timing, clear packets already loaded, just in case there are any. There wouldn't be any because this is our first time in. What does that look like? So it's not really a transaction, it's the whole connection. Zoom into the left, there's a SYN, there's a SYNAC, and we're down to very, very tiny times here. We're sub-millisecond. But the colours still come into play. So the colour of a three-way handshake is this olivey greeny colour. But I'll just reiterate about what these lead in and lead out colours are. And essentially what's that? This is the client-side capture. The packet was in the PCAP file at this time, and it was a client packet. So the server would have seen it at this time. The server would have thought about it for this long. The SYNAC packet would have left the server at that time, but we saw it in the client-side capture at this time. And then there's a rapid ACK. Just before we change the timescale, we'll see that there's orange followed by the yellow, which is normally the server time. Right click. Now at this scale, we're up to 6 seconds. So that very tiny orange at each end, we can't see anymore. But from here, the little grey line, what happened next? So what happened next was along the bottom. So what happened next after about 6 seconds was this yellow diamond, which is a final. So final, ACK, data packet containing a final as well, and then a red star is a reset. So this whole TCP connection, which was 6 seconds long, was SYN, SYNAC, ACK, final, ACK, data with final, reset. So there was no real work in that. It probably had no impact on performance, and that's why I said in an earlier video that these 400s in this capture are red herrings and we can ignore them. Except we might be curious about why the client would have sent them. It's one of the reasons I think this client in this case was a load generator, and perhaps just an artifact of the way that works. So the next thing I'd like to look at is some interesting retransmission timeouts. So now that we've zoomed in, I've talked about the pink squares before. There's one there, but these are the ones I'm keen on, and these are transactions that look like retransmission timeouts. So in other words, it's a transaction with the name retransmission timeout. Now this is in fact a pseudo transaction that NetData made up. And it did that because in the load data window we checked the box which said load high level transactions, and that instructed NetData to include the pseudo transactions that it can make. So we'll zoom in a bit closer there, and I'll zoom in even more. We can see there's actually two of them there. So let's grab the first one, right click, plot transaction timing. Now this time we will clear packets already loaded so that we can start clean. And in the packet timing chart we get just that transaction, and this nice bright purple, or Bob calls it raspberry. I'm a little bit colorblind, so it may well be. But that's just the transaction. There's our retransmission timeout. We can do the alt drag thing, find out that it's 203 milliseconds. But really we want to see the real transaction that's underneath that. Right click, load all packets and transactions of connection, and we get the full connection. There's the three-way handshake at the beginning. There's our HTTP GET. There's the real transaction behind the scenes, which is the mellow relive.jpg. And we see that this raspberry pseudo transaction is kind of on top of the real one. We go back to the transaction chart. Now let's grab the other one. So this time we right click, plot transaction timing. That's the same. This time we won't clear packets already loaded, and we will load all records of the same parent. So this will give us that whole connection again. It readjusted the time scale to the transaction because we were loading the transaction, but right clicking on the left and right edge, and here we can see there were two separate transactions and two separate connections with just one get each. We've already looked at the mellow JPEG, but the one underneath this one is get 4.jpg. Now the reason I want to point this out, there's two reasons. One, we can see how useful it is to have multiple connections on the packet timing chart. One is the client packets of that connection. 4 is the server packets of that connection. Row 2 is the client packets of that connection. And row 5 is the server packets of that connection. And you see how we've got the interesting is the server name, and if we click the addresses button, we get the IP address back. But it's definitely curious, in two separate connections and two separate transactions at two different times during the transactions, we got a retransmission timeout at exactly the same time. Now to get the flowchart, we can right click, plot flowchart of this connection. Now here's where the retransmission timeout occurred, and what's of interest is that it's packet ACK, and an odd packet all by itself. So it's a single packet all by itself, and 203 milliseconds later, a retransmission. So we can deduce that that's a retransmission timeout, quite a short timeout, pretty close to the delayed ACK, usual 200 milliseconds. So this would make us think, well, was there a push flag on that one? And yes, it's an ACK and push. Or the other thing we can do, format, turn on push flags, replot, and what we see is a little pinky purple right hand little attachment. There was a push flag there and there. So there's a push flag every 2 or 3 packets. So there's a push flag, but we had a retransmission timeout at 203 milliseconds, and then immediately a duplicate selective ACK. So right clicking out there. So there was a DSAC and then another packet. That packet made it to the other side, and the DSAC tells us that when we send it again, that was the second time. So back on the packet timing chart, the DSAC are the green diamonds. So do 2 DSACs and we can see the left and right edge of each one. So it would appear that the receipt of the DSAC caused the client caused the client to send the next packet in the sequence, and we'll just confirm that that's the case. Well, we can tell by the sequence numbers. IPID 465, 466, 467. Now it still took a while to get that ACK as well. So how far away was that? About 200 milliseconds. So in that case, this ACK is a delayed ACK to that packet, and it just happened to get in. RTO must have just got in before the delayed ACK timed out, but in this case the delayed ACK got in before the retransmission timeout, and then we're off. So the next thing I'd like to do, we'll look at the packet train pcap again. I'll drop that on, fast forwarded to get straight to the packet timing chart, and what I'm interested in is this area here where there's a red, it's an ACK followed gap. It's a DSAC, but it's red. I said DSACs are green, but this one's red because it's also a packet that follows a gap. Why is that an ACK followed a gap? Let's look at the sequence numbers. So the sequence number of this data packet ending in 1086. The sequence number of this packet is 1474. This packet was 194 bytes long. So I'll jump to this little spreadsheet that I made. Packet number 290 1086. It was 194 bytes long. Therefore, the sequence number in the next packet should have been 81280, but it wasn't. It was 1474, and that's a difference of 194. So what does that mean? Back to here, there's packet 290, and it's 194 bytes long, but there was 194 bytes of data missing. So there should have been about there should have been a black data packet 194 bytes long, and there wasn't. It was either dropped by the packet capture or it was lost in real life. And my money's on real life, because over here there's a green packet. Green means that it was a packet that filled a gap. This sequence number is 81280, and it's a 234 byte packet, and if you recall, the packet that was missing should have had the 1280 in it. So the sender has resent the 194 bytes that were missing there, plus some extra bytes to make it up to 234. The other thing to notice is there are these retransmissions as well. That's 400 milliseconds, 390. My money would be on those being retransmission timeouts as well. We've also got this very long time before that gap filling packet came on board. So we'll have a little preview at the flowchart now. So a couple of things I want to mention. One is that the flowchart can have client packets and server packets on it, and I'll talk more about that in the next video. Sequence numbers really should be viewed on the flowchart. And ACK gap is telling us, because normally ACKs don't display, but because this ACK had a gap in it, NetData is displaying in this spot. The height of that is the 194 byte that we're missing. And then over here, there's the green 234 byte packet that filled the gap in, and then we're away again. Just before we sign off, look out here, and here's another 300 millisecond retransmission timeout, and an unnecessary one, because there's another DSAC. Well, there's some extra features of the packet timing chart. Next will be the flowchart. Stay tuned.